yo-yo in a big circle like that, and so you got this yo-yo going in a big circular path like this, yes? Well, if you were asked to draw a free body diagram, you would never label centripetal force on the free body diagram, because centripetal force is like a general category of forces. Centripetal force is like the general name of the force that provides an inward force towards the center, towards the center right here. And basically, you have to think of what physical force is acting on this object right here, providing the centripetal force. So if we go back over here, in this case, if it's a yo-yo twirling around on a string, what would it be, Andy? Yeah, it would be the tension force. Okay, the tension force would be providing the centripetal force. So then when you go to do your formulas, F sub C equals mv squared over r. What you'll be substituting in for the centripetal force is the tension. So then the centripetal force here becomes the tension, and therefore the tension is going to equal mv squared over r. All right, let's look at another example here. Let's say you have, overhead view of a car going around a circular track. All right. Overhead view of a car going around a circular track. Now here's the thing, if the car is going in a circular track, we know there has to be an inward force acting on that car. So we know that there's this inward force acting on the car. The question is, what physical force is actually there providing the inward centripetal force? It's not like last time. There's no string that's pulling in the car as it goes around here. Okay, there is no string like that. So, question is, what is that centripetal force? What is the inward force that's actually there? Believe it or not, it's actually a static friction force. Static friction force. Even as the car is going around and the tires are turning, on a tire, as the tire comes around, the surface actually like let's say this is the tire. The tire comes around and touches the road right here, and then goes around again and touches the right here, and then goes around and touches right here. The tire is actually not sliding against the road. It's just actually being like laid up right against the road. And it's actually a static situation. And what's really going on is when you turn your tires a little bit, your tires end up pushing on the road. They actually push on the road outward, but you can't have tires push on the road outward without the tires doing what? It's a third law thing. The tires can't push on the road outward without the road doing what? Pushing back on the tires inward. And that's what's providing that centripetal force. The road is actually pushing the car inward. So it's actually a force of static friction. Who knew? Now, this is a little bit different, folks. Normally, we think of, the car moving this way. And we think of the friction force, acting in the opposite direction. Yes? Back this way. This friction force over here is not the friction force I'm talking about. This friction force here is the air resistance slowing down the car. This friction force over here is the rolling friction force. I'm talking about this friction force right here, which is a sideways friction force, which keeps the car on the road. So if you're doing this particular problem, and you go and you write your centripetal force formula, F sub c is equal to mv squared over, whoopsie, I guess I can't go out of that there. F sub c is equal to mv squared over r. Well, in this case, what you're going to be substituting in for the F sub c is the static force of friction. Does anyone recall from last chapter what the hidden rule for calculating the static, David?
It's the coefficient of friction, static friction, and the normal force.
Yeah, what do you have to do with the two of them? Yeah, you multiply them together. Yes? And what is that normal force equal to if the car is on a flat horizontal surface? The force of gravity. Okay, so basically this becomes force of gravity. And what's the force of gravity equal to? What's another expression I could put in for that? Deanna? No. The mass times gravity, exactly. So this equals m times g. So back over here with this circular motion formula, this becomes m times g equals, I'm sorry, what did I leave off here over here, folks? Oh yeah, the mu sub s, mv squared over r. So that's better. It gives me a little more room, I think. All right. Now, how do I get back? All right, so if you take a close look at that, folks, basically I'm just going to repeat myself here for a second. The centripetal force is equal to mv squared over r, and the centripetal force is actually provided by a static friction force, which is equal to mv squared over r. And basically, the static friction force is equal to mu sub s times the normal force, which is mv squared over r. And then this becomes the static friction force times the weight force, which is mv squared over r. But the weight force is equal to m times g. And do you notice what happens with this whole situation? Lena? Yeah, the m's cancel out. So it turns out that basically how fast you can make that corner doesn't depend on how heavy or how massive the vehicle is. It depends on the radius of the circle, and it depends on the texture between the tires and the road. Yeah, if there was ice and that coefficient was low enough, if there was ice and that coefficient was low enough, let's see, can I go back to that? Then let's say you're coming around, here, and then at this point here, if it was all ice, your tires might be turning this way, but they would just be sliding forward, and what you would end up doing is just going right off tangentially. You wouldn't be able to make the turn. That actually happened to me once. I was driving along and hit an icy spot, tried to turn, couldn't, and I went right into the guardrail and ended up getting a speeding ticket. Not that I was speeding, but he said I was going too fast for the road conditions. And then I talked to him at the court hearing, because believe it or not, I was just going to plead guilty and just hand it in. But talking to like friends and family and relatives, you never ever ever plead guilty and just send your ticket back. You always go to the court and plead non-guilty. And 9 times out of 10, you could talk your way down to a lower deal. It's like all negotiating. And basically, I talked to the police officer and I said, look, I got a clean record, never, blah, blah, blah. And so he lowered it to a ball tire ticket. And I didn't even have ball tires, but that's what we lowered it to. Pardon? No, that means when the rubber surface doesn't have those grooves, so it's like flat. They're called slicks. Then basically bald. Okay, Ashley.
How do you know what
That's a great question, and that's what I'm trying to show you here. You have to just look at the picture and ask yourself, what physical force is there doing the job? In the first case with the yo-yo, what was actually there providing it? That string was pulling in, so it's a tension force. In this case here, it's a car going around. Okay, so then you have to say, what is it? Now you know, if it's a car, it's a friction force. And we're going to look at a third case, and basically these 3 cases are the only 3 cases I could think of. For right now. Later on, we're going to learn more.
Like, if the wheels are going kind of diagonally, why isn't the centripetal force like a component of it?
Okay.
It's not going directly to the center.
Well, the wheels, say the car's like this, yes? And the wheel is going to be like this, like my hand. And the car is pushing this way, yes? And so it's pushing the tire this way, yes? But basically, there's a component of that force, which is this way. And that's the component of the, force that the road pushes back. The other component of the force going this way, Dan, is this way, but what does the tire do this way? It rolls, so there is no pushback force in that direction. So, okay, here is the car right here, yes? And here is the tire, okay? And the tire is being pushed this way. And basically, if you break that down into components, okay, part of that force is acting this way, part of that force is acting this way. This part just pushes the car forward. This car here pushes on the road perpendicularly, and then the road pushes back, which pushes inward towards the center of the circle. I don't know if that clarifies it at all. I don't even know if I got to the essence of your question.
So then wouldn't the opposite centripetal force be diagonal too? Like opposite since the tires are pushing outward.
Outward.
Then wouldn't the centripetal force be pushing inward as it?
Inward. Inward, which is straight in towards the center.
Oh, so it's not pointing diagonally out.
No, the one that's going out is going directly perpendicular to the tire, straight out.
Yeah.
And then the road pushes straight back in.
So it's just okay.
Yeah. Yeah, those masses cancel out. Whoa, we need that to cancel out. note to anyone listening, the mu stays. Okay. All right. So, all right. So, third kind of force. Okay. Here we go. All right. Okay. So let's say we have, you know, okay, we have the sun. Okay. Okay. So, this is getting ridiculous, kid. Okay. All right. And then you have some other planet, and the other planet is going in a circular path around the sun. Could be Earth, could be Mars, could be any planet, yes? Okay. So the planet is going around, and it's actually an elliptical path, but it's so nearly circular, to the naked eye, it actually would look circular. You know, if you were just actually, you could see the path. So we know that there's this inward force acting on the planet, providing the centripetal force. There's this inward force acting on the planet. Well, what's providing the centripetal force in this case? It's not a string. It's not like the sun has a string and it's like, whoa, cowboy, you know, where are you going there, little heifer, you know? And it's not like there's some kind of like steering mechanism that's like pushing off the atmosphere, you know, or space or whatever. So what is providing that force? Miguel. Yeah, the force of gravity. The force of gravity is acting on that planet, pulling it inward like this. Now, of course, there's a third law thing where the planet is pulling on the sun just as much in the opposite direction, but we're not too concerned about here. We're just concerned about what's acting on the planet there. So in this case, when you go to write your F sub c equals mv squared over r, okay, it's going to be, the force of gravity equals mv squared over r. But what's the expression? What's the formula for that force of gravity? Alex? Oh, that's coming. We're going to get back to that one soon. Okay, but what's another one? Right. You could use that one. If you know the mass of this planet, you know, say this is M1, and you know the mass of this sucker, M2. I'm sorry, mass of the star and mass of the planet. Yes?
The gravitational constant times m1 times m2 divided by.
Yeah. What's interesting, when I'm writing, you see I have a shadow there? So the light doesn't go through my shadow. So I'm actually like, I can't see what I'm writing until I move my hand away. I don't know if you can tell, you know what I mean? Like, you know, it's like I write something, and it's not there until I move my hand away because my hand. No, look, right, watch. I'm writing on my hand here, see? And then I move, and then it's there. But it's kind of weird. It's like driving with your eyes closed, and it's not Not. All right, now I'm being dramatic, but you know. All right. Okay. That's kind of fun. Look, you can follow the ball here. F. Let's get my hand. F equals G M1 M1 M2 all over D squared. Yes, it's true. You know, like how you follow the ball as you gravity. Okay. So we can apply over here F sub G. We know that that's going to be G M1 times M2 all over the distance between the two of them squared, and that equals mv squared over r. Well, here's the thing. You see this distance? The distance is basically from the center of one to the center of the other. From here to there, yes? So what's the deal? If that's the distance right there, what's the deal with the difference between the distance and the radius of the circular path that the object's going through? Those two are equal to each other, yes? So here, D, the distance between the center of the two, is equal to R, the radius of the circular path. So basically, this D could become an R. So it's G, M1, M2, all over, R squared equals mv squared over r. So you could simplify that, and one of these r's can cross out with the square. Dave?
Which mass is it talking about in R?
That's exactly what I was going to go talk about. Okay, what about this m right here? Which mass is this mass over here? Yes? It is m2. This mass is always the mass. This mass right here is always the mass of the object that's going on the circular path. Okay? So this is the mass of the object going on the circular path. So this here is actually m2, 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 m2. And we see that m2 cancels out. And, you have another hidden relationship. I wouldn't memorize these down here, folks. I would just say, hey, I know my big papa formula right here. Woo! Yes? The overall inward force is equal to the mass times v squared over r. And then I would ask myself, what is actually providing that centripetal force? Finally, I want to focus more on this last force. This inward force due to gravity. And Alex, this brings up that other formula you brought up. Because you were right. You were right. I just wasn't going there. But I'm bringing that in now. Okay. This force, folks, you could really write down 3 expressions for it. So, one, we know that the weight force is providing the centripetal force. So it's equal to m2 v squared over r. But we also know it's the force due to gravity between the two masses. So it's Fg equals g m1 m2 over r squared, because r and d are the same. But then Alex brought up that little blast from the past. Remember how the weight of an object is equal to the mass of the object times the acceleration due to gravity. So that's another expression for that inward force. Now, we know that the mass of the object always stays the same, no matter how far away from this object it is. The amount of mass, the amount of stuff that this particular planet here has stays the same. But what about the weight of the object? Does that stay the same as the planet goes farther and farther away? It's going to be less. It follows that inverse square rule. Do you remember that? Like, if you double the distance between the two, the force is going to be 1/4 what it used to be. If you triple the distance between the two, it would be 1/9 of what it used to be. So if the mass here is always the same, but this force here varies, and as you go farther out, it goes with that inverse square rule, then what's the deal with the acceleration due to gravity? Is that going to stay the same whether you're here or out there? Danny? It's also going to have to change. Look, if the mass stays the same, but this does the inverse square law, then this has to do the inverse square law. So you know how we say, like, on the surface of the Earth, g is 10 meters per second squared? Well, if you went to 2 Earth radii, then guess what the acceleration due to gravity is going to be? Dina? Well, it's going to be double the distance. So if it's double the distance, so if the distance is doubled, the force is going to be 1/4, because the doubleness, the 2 gets squared, so it's going to be 1/4 of what it used to be. And if it's 10 here, it would be 2.5, 1/4 of 10 out there. You follow me on that? So here's the thing, folks. You see these 3 formulas right here? 1, 2, 3. These are 3 formulas you have to have memorized. Stay with me, folks. We only got like 4 minutes, 28 seconds left. But this is crucial stuff here. I'm going to actually go to another page here. Okay. Let's say you have some unknown planet, and you're given the mass and the radius of that unknown planet. Yes? And you want to know, hey, what's the acceleration due to gravity on the surface of this planet? It's not going to be 10 meters per second squared because it's not the Earth. Well, remember those 3 formulas? Yes? You could pick and choose, and since they're all the same force, the 3 right-hand sides have to be equal. You could pick and choose any 2 right-hand sides of those 3 formulas and set them equal to each other. What I'm going to do is I'm going to choose the formula G m1 times m2 all over r squared equals m2 times g. If I choose this right-hand side, and I choose this right-hand side, look what ends up happening. The m2's cancel out, and I'm left with a nice handy-dandy formula for calculating the acceleration due to gravity on that unknown planet. Hey, I want to know what the acceleration is. Take that universal gravitational constant, multiply by m1, divided by the radius of that particular planet. Oops, thank you, squared. You want to memorize that formula? Sure, go right ahead. But you know what? You have enough to memorize. Just remember those 3 formulas for that inward force. And remember, you could choose any 2 right-hand sides and put them together to whip up new formulas. Last case. It's going to take too long here. Let's say that there's another little planet. And now this is my R. Let's say I want to know, hey, what's that just right velocity that that planet would have to stay in orbit? I know if it's moving too slow, what would it do? If it's moving a little faster, but if it's moving at just the right speed, falling, 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 staying in orbit, yes? Of course, if it was going too fast, hasta la vista, baby. Let's say I want to calculate that just right velocity. Well, remember those 3 formulas that I wrote out for that inward force? This time, I'm going to pick these 2. What is it? G m1 m2 all over r squared equals mv squared over r. Notice, this is m2 here, so that cancels out with m2. This r goes with the squared. If you solve for v, what are you left with? The square root of g m1 all over r. Another handy-dandy formula for calculating that just right velocity needed to stay in orbit. You can memorize it if you want, but you could always whip it up from the original 3. Okay. That added an extra level of stress using and being recorded.
Yeah. Huh? Yeah, that's what we do. Is it still recording?
Did you hear like a song happening at all?
Yeah.
It's still recording.
It is? Great. Is it?
I didn't see it stop.
We're still on. Oh, man. Yeah, Andy, did you see your physics notebook? Did you see your physics notebook?
Yeah. I'd like to save it all up so I get